Okay, so just to start, where to find LapSim, and it works like any other CAD. It's in GitLab or GitHub, excuse me. So just like you have like Active CAD or CAD Workshop, there's a repo named architecture-lapsim. And this is where LapSim is stored. This is where I've been putting weight analyses in here, as well as there's some like historic data in here too. So yeah, GitHub repo architecture LapSim, and then there's a folder LapSim, and then there's a couple of versions in here. So the most up to date is V4, and that's what I've been using over the last year-ish, year and a half, I don't know. But yeah, so everything's in this Lab Simulator V4. So get that all downloaded, and then once you just have all this stuff, there's only some files that you need to like have open. A lot of these are just like files that MATLAB uses in reference while doing calculations, but I'll show you the important ones to like change and run. Okay. All right, everyone can see MATLAB, yeah?
Yeah.
Yes.
Cool. So first off, what I would recommend anyone that's looking at running MATLAB at all or running this LapSim at all do is read through the documentation on the website on it. There's really great documentation that Max put together on this program on the website. Gives a good overview of how it's functioning. And I think that's like the easiest like first step. Obviously that being like forward facing and not or like public facing and not like internal. There's more information in the actual files, but I think that's a really nice, like simple, like start your understanding of how LapSim is doing its math. And I'm definitely not really fully qualified to like explain all the details, but effectively it actually like calculates in reverse by steps throughout the lab. It's not like time-based, but like position-based. So, and that's what you want, obviously, if you're going to be evaluating like lap time a lot of the time. So the first, like the main files to have open are the ones I have here. So there's like three main like I would call like files to run LapSim, and that is run LapSim, pretty straightforward, LapSim function, and sweep lap. And we'll go through and we'll start simple and move more complex here. And then beyond that, there are vehicle models. So the way LapSim works is it has this function, LapSim, and plenty of sub like functions and files. But you can run any vehicle model through the simulator at any time, which allows you to like do comparisons. For example, you could compare a architecture of, in this case, I could compare 2018E to 22E. And I'll go through like some of this stuff in a bit, but effectively you can create car models, and what you want to do like generally every year is create a new car model, like bring it up to date as much as you can, and use that for your evaluations. I actually already have made a 223E because when I was doing monocoque design and evaluating static weight distribution and wheelbase, I wanted to compare it to this year's e-car where we would be like using the new monocoque. So there is already a file in place, but obviously like things are going to change as we like develop the car further and might want to like refine some of the parameters as they are like generally like 222 parameters, just kind of carried up because obviously I couldn't have foresight into exactly what the vehicle was going to look like for this year. So yeah. And please, anybody jump in if there's questions at all. I'm going to try and keep it relatively brief and like high level, how to run it, how to get cool graphs and useful graphs. But yeah, I also don't have like 100% extensive knowledge. Like there's stuff in here that I don't understand how it works, and there's also stuff I don't know how to use. So I'm just hopeful that this kind of like little intro will get you through the first couple of days of like messing around, looking through files, trying to figure out like what file runs and what command does what. Because yeah, I don't know, it took me like a couple of days of just like actually dedicating time to this to figure it out and just figure out how to make it go and do sweeps and stuff like that. So hopefully just trying to eliminate that as time you guys have to spend on it. Okay, so to start, there's a good introduction in the LapSim function file, and it talks about how it's doing its math, and I think it's somewhat helpful to understand a little bit how it's running. So effectively, it's like a 4-tire model where it can run this vehicle through different tracks. So currently the one we have data for is 2017E, I believe, autocross. And then Excel, obviously being the simplest. But if we in the future want to like update to a newer track, that's also possible. It's just someone has to map it and do the work to convert it. So yeah, effectively it calculates the forces and velocities relative to the body, but at every like corner. So we can look at things like tire utilization and forces on each tire separately if desired. Yeah, so that's just the super highlights. Yeah, some good stuff to point out in here. This is like obviously not considering driver like ability, effectively just using a optimized perfect driver. So that's something Max talks about here. Yeah, and this is not a perfectly like holistic model. Obviously, we're not modeling every single thing in here, and there's like work could be done to increase the accuracy. And if someone wants to take that on, that's great. We should encourage that. But yeah, so just like understanding its limits means that you can make good decisions based on the data. So some important stuff that I'll call out like right away that this doesn't do. For C-car, most importantly, it does not do torque/power curve lookups. That means, right, like at any given velocity, it's not, or like velocity translated to RPM, it's not looking up the vehicle's torque and power and applying that across the in this case, rear axle. It's simply always operating at peak, which is really not ideal for C-car, but this was designed for E-car, which is a lot like less, it's a lot less of a incorrect assumption, especially because like torque power curves for the E-car are a lot simpler to implement into the LapSim rather than the combustion engines. So similarly, no shifting. There has been some work to implement it. I'm not sure if I'm pretty sure it's not running in the main version here, but there are like graphs that can be found with shifting. But yeah, and then there's stuff I just don't even know. Implement electrical systems processing. I think that's like losses with respect to the inverters and stuff, because there is losses in here with respect to like the drivetrain. And then, yeah, buffer fractions, so start speed equals end speed. This is only relevant if you're running multiple laps. But yeah, typically I don't run multiple laps, not really necessary. Cool. Questions? Okay, continuing. So when okay, normal MATLAB things, make sure you're always within the correct folder, otherwise it won't work. But this is like this file run LapSim is like the easiest place to just like start understanding how to run it, LapSim. So there's a couple different ways you can run it. Like anything in MATLAB, you can like uncomment this and then run the program. But you can also just like copy this into the command line and run it from the command line, which is, I don't know, typically how I do it, because I like to like iterate it quickly and not necessarily edit like how the file is working a huge amount. So first thing I'm gonna do is, so something to take into note is when generating all the plots and doing lots of runs, it can be like time intensive to get results. So I'm going to just do a simple first run to show you guys. So because I want to do a couple different runs. So for example, this run sim lap car is what car you're running. Pretty straightforward. It's mainly explained here. So we're running 218E plots. We're turning off, so we're not going to generate any plots. We're just going to look at the math or the data for a second, and then Excel only. So if you have this set to true, it will only run Excel. Pretty much you can run Excel and autocross, and that's what we generally care about the most. So autocross being the most important, obviously. There are also defaults in here, which I have set. So like if I forget to put in a lap car, it will auto default to like the newest car and stuff like that. It'll also default to running autocross, stuff like that. Nothing crazy, but I find this is helpful to actually vary this. In that case, like while I'm running sweeps, I don't have to like go in and like always have to write out all of this if I'm like making a new sweep or something. But yeah, so we'll just run this. Okay, so the output goes into this structure called answer, classic MATLAB, which is over here. And this is like the raw data that it's outputting. For like looking at graphs, because this can do a lot of graphs, I think it's helpful to look at stuff like this because, you know, at the end of the day, you might be like, oh, well, I just ran the 218 through Excel. How long did that take? And that's stored in the time variable. You can also just like command it to answer this, but just looking at the data, okay, we ran Excel in like 2.7 seconds. Wow, that's quick, but like decently accurate from the Excel times that I've seen. We can definitely hit stuff like that. But yeah, also always to note, right? All models, you know, all simulations like this are wrong. Some are useful, which means, right, like every time we run the 218E, it's not going to put down this lap time, right? Like there's inherent error and lots of stuff not being considered. Anyway, yeah, so you can look at data for any of this stuff. So we can look at like the aero drag data and a bunch of other stuff, curvature of the track, etc. Should just be like constant. Yeah, no curvature. Cool. So now we're gonna do the same thing, but I'm gonna turn on plots. So you're gonna see it generate a bunch of plots, and by a bunch I mean a bunch. You can like turn off some of these if you don't like want to see them all, but for this demonstration purposes, I am going to just show them all, kind of show like what the variety of things you can look at is. Not all of this is like super well set up. Sometimes there's like code in here that people added to do like one analysis, but maybe didn't remove or like add titles to. So then you either have to know what that is, or you're gonna have to go like dig into the plotting function and like see what it's actually taking as inputs. But generally, like you can, yeah, like not everything it displays is essential, and you can go and like on your version, like not have all these plots generate and just whatever you're interested in. So, for example, this is tire normal force with respect to speed. I'm not going to go through all of these, but stuff like contact patch force versus speed. And this is specifically evaluating like some different power usage on the front and rear axles. So it's like, okay, like what power, so this is what this is telling us here, right, is like the optimal power on the front axle is really only 17.25 kilowatts. Obviously, that's like, this is the justification of like why we could run smaller motors in the front, because, yeah, you don't actually need all the power across an Excel run, which is a great place to look for power. Yeah, anyway, like here's an example of one that's just like not labeled at all. Someone was looking at something and it's just in the code still. Effects, so forcing the X direction from the tire in Excel. Yeah, bunch of stuff. I'm just gonna like go through most of these. If there's an interesting one, I'll pull it up. This is your like direct longitudinal mu. Obviously for Excel, it's also in a straight line. Once we do autocross, it'll be a little more interesting. But yeah, no yaw moment in Excel, unlabeled. yaw moment diagram, 0, but that'll be more interesting. GG plot, kind of expected here, really rearward shift to GG while we're accelerating and nothing laterally. Tire utilization, stuff like that. Anyway, we're just gonna get out of there. Okay. So yeah, now, just because it takes more and more time every single time we do it, let's run. Why don't we go 3E plot on for autocross? Oops, I don't need to do that. This will take a second to generate. And like, remember, this is only running a single lap. So as we, let me just check. Okay, not something I'm going to open. Great, now I've lost my stack, but yeah, so some not exciting things, some exciting things, contact patch force versus speed. You can see how there's like a maximum like power effective that we can use. Someone's joining, probably Josh. Oh, it's Amir. Hello, Amir. Yeah, so interesting stuff to see like throughout an autocross lap, how we're like utilizing contact patch force in the fronts versus the rears. So obviously the rears can take a lot more force, or seeing a lot more force than the fronts. God, so now this is a problem where I've unstacked it. I'll just get rid of the not exciting ones. So stuff like tire longitudinal force per corner, some interesting plots. And yeah, total hub power. So this is like how much of the power available to us are we running in any given spot along the lap. So you can see right on the long straights we're at 100% hub power, running at the limit, giving it everything. But then in like a sharp corner, we're like, either braking or coasting and not necessarily like using power. So yeah, cool plots. And this is what the track looks like for 217E. Lateral acceleration, also just super cool, but I'm gonna kind of just breeze through these. So there's a bunch of really cool stuff. I suggest running it and just like looking through every single graph that's automatically generated, because a lot of them are really interesting. That one's not. And then here's a great one. This is like the LapSim GG plot, which obviously is like a classic vehicle dynamics plot that we should be using and evaluating. But yeah, this is how the LapSim interprets the results. So you can see it's a lot more like square, and that's because another limitation of the LapSim is we're not using like accurate tire models. We're just effectively always at the tractive limit of the tire, and it's a relatively simple tractive limit that's not varying with temperature, not varying. Yeah, so something else that we could improve on if someone wanted to take it on is implementing like a more accurate tire model. And I actually have some links for that I've seen people do. Yeah, anyway, cool stuff. Let me just get rid of this. This is the only problem, is it generates like heck of plots. All right, so yeah, that's like basic running. Just can input stuff into the command line, run things from the run LapSim. So now before we jump into what's I think the more helpful function, which is sweep lap, I want to look and break down the like a vehicle model. So a vehicle model is what's being run, right? So effectively, it's supposed to characterize your vehicle in terms of what's being considered within the simulation. And this is where you can like get to stuff where you're updating a vehicle model or you're like sweeping with these parameters across the, I want to see what the effect of, vehicle drag is on lap time. And when, by the way, even when graphs are on, all the answers are still output into the answer stuff. So in that autocross lap, we can go see what the 2023E would have been running. Where's time? Theoretically, across that lap, we were running like an 82-second lap, 81, excuse me. Cool. So yeah, so 222E here, for example, and most of these are the same, although if you like some of them I have added things to, and generally I'll make a note where I add things. or sometimes I don't, and I've just like added some more accuracy into the model, or just like some math. So it's like easier to implement. I've also added a lot of notes. So if you look at these, like all of these like arrow terms in some of the older ones, they're like not defined. But yeah, so feel free to, reference the newer files. Will have a little bit more information in them, where like, I was going through this trying to figure out stuff, and lots of it's like pretty self-explanatory, but just make sure you understand what's going on. So a couple of things that are evaluated: vehicle mass and CG location. So height and longitudinal location. Chassis, lateral load transfer, track width, front and rear. So something you can look at is varying track width. Wheelbase, something I've looked at a lot. Yaw inertia, brake bias split, and dynamic brake bias split. So there's a couple things in here that are like things that were added into the simulator to evaluate their effectiveness. Like, do we want to have on dynamic brake bias, and like how valuable that is to us, right? Because like toggling this on or off, looking at it, and then being like, okay, like, is this something worth putting our time into? So another one, obviously, that I've talked about a lot is like active aero, which is implemented in the LapSim as well. So jumping into aero, how that works a little bit is there's a high and low version for every, for your CL and CD, coefficient of lift, coefficient of drag for my non-aero teammates. And what this allows you to do is, as well as like some basic other aero stuff. So frontal area, and then like aero balance, so like the position of your center of pressure. And yeah, air density, fun stuff. So how this works is there's a little bit of detail in here, but turning on active aero, and then the factors that like how often the active aero is activated. So how often are we switching from the high to low drag states? And you can see that here. So like high is like what we typically are always running in. And then low is what, it's like, all right, if you trim out the wings, like this is the force above the sea. So to have an idea of this evaluation, for example, you would want to have these values and then run this and then see how, how much lap time you gain. You can run one with it, active and one with it out, and then just directly compare lap time. Like I was showing in the answers. Tire stuff, here's your like really basic tire model. And then propulsion, it's also relatively basic depending on the car. This is being an e-car, has the motors in here. And for some reason, it's only done front and rear. And yeah, so I've added some of this math stuff to just calculate it based off of some of this gear ratio. So if you wanted to evaluate changing gear ratio for the electric car, for example, or the combustion car, you can do that. Yeah, actually, I don't have gear ratio implemented. So yeah, and then top speed. So kind of like relatively basic stuff. And I think it's helpful to see like what we aren't evaluating, right? We're not evaluating things like lookup tables for the powertrain or like suspension dynamics, but that are things that could be implemented, or like better aero mapping, right? You could have all of these as functions of vehicle speed. If you're looking at how does your aero, if you have the aero map created where you can like look up your CLCD with respect to ride height and vehicle speed, like, so there's a lot of improvements that could be made, but it's generally a really helpful tool. So going from there, this is how a vehicle model is set up, how sweep lap works. And there's an example up here. And I have a couple of examples down here. I've also logged, these are the ones I used to generate some of my plots that you probably all have seen in my like senior design for monocoque stuff. I've logged them here just because it's kind of like an iterative process. You want to start with big steps to kind of like make sure you're grabbing the area of the graph that you're interested in, but you don't want to take a jillion little steps every single time, because you'll see this will take a minute to run, because every step you're taking where you're varying parameters, right, is running a lap, and you saw how long one lap took to run. So once again, there's baselines in here. But yeah, so just grabbing a basic one that I actually just put in here earlier, just to see how this works. So in this sweep lap, the first, you can change 2 variables at a time, so variable 1 and variable 2. And what this is going to do is going to overwrite the variables that you have set in your vehicle models. So in this case, we're going to vary mass, and so we're going to do it. And because I haven't specified a vehicle here, it's going to do whatever the baseline is in the file, which is 223E, excuse me. So you can see here for the mass, it's set at 277.3. And I'm going to override that, and we're going to evaluate from 200 to 300 in steps of 25. So your basic like programming array. And that's obviously really coarse steps, but that's because I don't want this to take forever to run. But even if you look at that, right, like within that, we're running 5 steps. No, just 4. Those 4 steps is what's going on right now. It's running those 4 laps, and then it will like correlate put all the data together and present it. So a lot of times there's a lot of like, yeah, so now you see why like you don't want to just go straight for a super precise calculation, because it will take a hot minute to get all your information. So this is relatively straightforward. We're increasing mass. So as mass goes up, what do we see? The energy required. This is used for accumulator capacity selection. Goes up. Understandable. Similarly with time, as this is like our sensitivity to time with respect, or sorry, excuse me, our sensitivity to mass with respect to time, right? So if we can drop our car to 210, we can hit, you know, in this lap simulation, we can hit about a 78-second lap, where if we're up at, you know, 290, we're going to hit an 81.5. And that's like a, you know, 3.5 second. Obviously it's a lot of mass, but difference. So kind of can help you make decisions on what stuff is worth adding. Cool, pretty basic. Once again, you can adjust like what output it's given to you, or it will go into the answers. And you can look at direct values as well. So that's like the basic version. You're running one thing, you're sweeping one thing. And there is more advanced versions where you're sweeping multiple things. So all you have to do that is include your like second set of variables in the sweep. Let's see. I'm not sure I have a great one for this. Usually it's fun to like grab something that will look cool. This is dangerous because I don't actually know how long this took to run. 0.05. Yeah, I'll just vary this one to be safe. Okay, so simply all you have to do is like add what your second bar 2, whatever you're going to vary next. And then for this case, we're going to vary mass, and let's vary I don't know what'll generate anything fun, but we'll just do like wheelbase or something. Actually, I know what these generate because I have them saved in my file. So for example, if you were to run, I'm not going to do this because it's going to take time, but if you were to run this, so sweeping wheelbase across these numbers for like the length of your vehicle, and then your CG location, so this is static weight distribution across these variables, it will output stuff like this. And once again, just simply not doing it for time because this like took minutes and minutes to run because you're running a huge amount of laps, right? So every like X and Y coordinate within this is, then every step is a run. So it takes forever to run. But you can get really good, interesting graphs where, for example, we're looking at vehicle wheelbase and static weight distribution front across your vehicle. And this is how I was able to select what we built the cars for this last year. So like 1.6 meters, which is our wheelbase, and a static weight distribution of 46% front. So that puts us right up here in this like lowest time zone, for example, right? So lowest time of less than 81-second lap time. But it also is like helpful to see if our static weight distribution is like way off and our wheelbase is way too long, you can like, how much time is that adding to you? Okay, it's really only adding like 45 seconds. So it's not like super sensitive. Obviously you want to optimize your vehicle as much as possible, but if for packaging reasons you need it to go one way or the other, for example, you can make that trade-off here and evaluate it.
I got a question about that.
Yeah.
Why did you decide to go with the 1.6 and not go higher if it's still within the like fastest laps? Because like just from looking at it, like you're kind of at the point, and wouldn't it be easy to kind of fall outside of that lap time, or like why?
Yeah, that's a great question. So what's not what's important to like, with this analyzing this graph is like, what are we not also sweeping that would change with these things? So for example, what's not being considered here at all is vehicle mass. So vehicle mass is being held constant, but it's relatively easy to understand that as you're going to increase the length of your vehicle, you're going to increase mass. So the idea is to like, for this graph to hit kind of like the bottom of this low time peak.
Okay, that makes sense.
That makes sense. Yeah. So, and like you can get really fancy with it. And I did do some fancy stuff for these graphs. With like, if you want to try and like get an idea of how your mass will change with respect to wheelbase, for example, like, what does that mean? Obviously that's like a little bit outside of the scope of the LapSim. Like it won't generate that for you, but if you could correlate this to vehicle weight, you could then implement that as math, calculated values within the code. And that would increase the accuracy. So actually that's one thing, this is the 223 model. That is one thing I did, if anyone remembers me talking about it a lot with like Justin and people, which is, for example, although vehicle mass is not changing with respect to like wheelbase, I am changing yaw inertia, which would be affected a lot higher. Right. So like not only is your mass likely going to go up with a longer wheelbase, but your yaw inertia will most definitely go up. Even with a constant mass car, your yaw inertia will go up. You could build a longer one with the same weight, your yaw inertia would still go up. So I instead did some correlation within like the static weight distribution and weight analysis spreadsheets to determine approximately like what that relationship is. And for our like wheelbases, it's like decently linear with like a slope of this, more or less. Obviously an approximation, but something to increase the accuracy of the simulation, because like running it without it, if you got to pick where you want to make your trade-offs. It's like yaw inertia is going to change a lot. If you're not going to evaluate that, like how much does that throw off your vehicle speed? And yaw inertia being pretty important and varying a lot with wheelbase, I decided was like relevant enough to go for a calculation based off of your wheelbase sweep. So yeah, that's kind of how this thing works. Is there any other questions? It's really not too complex once you kind of understand how to run things and like what does what. I think it can be really daunting when you like open up this folder and there's just like a billion files. Oops, one more of like different stuff, and you're like, all right, well, what's important? and ultimately kind of what's important are the vehicle models, and then run LapSim, LapSim function, and sweep plot.
Would you be able to put those in like a separate folder so that we know, like, in case we don't need to rewatch this video to know exactly which ones to open up?
I mean, ultimately, you can technically like run them all without folder. But yeah, I'll make, when I put this on the wiki, I'll like put a little page together that's just like basics. Like here's where I'll put where it is and GitLab and something like that. So cool. Questions? Kind of simple, but hopefully it gets you started.